Imagine building a music application that catalogs thousands of songs from hundreds of artists. With such a large amount of data, quickly retrieving information on specific artists or songs is essential for a good user experience. Suppose a user wants to find the artist for a particular song. One approach is to create a large array of song objects to store the song titles and artist names. Then, starting with the first element at index 0, look at each song object in the array until you find the song you're looking for. However, because the application contains thousands of songs, searching for the right song will take a long time, which could frustrate your end users. A better solution is a hash map, which rapidly locates items in large data collections and is much faster than searching an array. In this video, you will learn the basic concepts of the hash map type and the benefits of using it when you need to find information as quickly as possible. Before you learn about hash maps, it helps to understand the concept of an identifier, because they are fundamental to how hash maps efficiently store and retrieve data. An identifier is a string of characters or numbers that uniquely identifies a person, place, or thing. For example, when using social media, you have a username that is unique to only you. That username is an identifier. So what is a hash map exactly? A hash map is a collection of key value pairs. A key is a unique identifier of some kind, such as your username or national ID number. A value is the information associated with that identifier, such as your social media profile or personal information in a national database. How can a hash map be used in your music application? Each song in the music application has a key and a value. The key is the song's title and the value is the artist's name for that song. Consider the song Satisfaction by the Rolling Stones. In this instance, Satisfaction is the key and the Rolling Stones is the value. In other words, the song title is an identifier that can be used as a key, while the artist or band's name is the value. Now imagine if the application you're building contained 20,000 songs. There would be many songs and artists to keep track of, so you would need a hash map to retrieve a song's artist as fast as possible. To demonstrate this, let's create a Java application called SongMap with a main method that can be executed from the command line. Import the hash map type from the java.util package by typing import java.util.hashmap. Remember that because hashmap is a Java class, it uses camel case for its class name. The next step in the body of the main method is to create an instance of the hash map type. To do this, create a variable called map of type hashmap with the new keyword and a hashmap no argument constructor. This line of code creates an instance of a hashmap. Once the hashmap instance is created, you can add song titles and artist names. To do this, use the put method, which requires two parameters, the key and the value. In this case, the song title is the key and the artist name is the value. The type used for the key and value are both string types, but they do not have to be. Keys and values can be different class types. Add a print statement to put the contents of the hash map. Finally, run the Java application so it will print out the contents of the hash map instance, which should display the song titles and artists like this. Notice that an equal sign separates each key from its value. In this case, the song title and its artist, and that a comma separates each key value pair. This is the default print format for the contents of the hashmap type. You may also notice that the order of the songs and artists in the hashmap is not the same as the order in which they were entered. That's because a hashmap is not an ordered list like an array. The order in which you add items to a hash map does not affect their storage order because hash maps are designed for quick value retrieval, not for maintaining an ordered list. The keys used in a hash map, in this case song titles, must be unique. Adding two songs with the same titles will result in the first artist's name being overwritten by the second. For example, if you add two songs titled LOVE as shown, the song LOVE with the artist, Alvin and the Chipmunks, we'll have the artist changed to Nat King Cole, because only one artist's name can be associated with a song title. In this example, the assumption is that song titles are only associated with the original artist, and that two different songs can never have the same title. In reality, the world is very different. Cover songs, where a song is a new recording by a musician other than the original, are common. However, for the purposes of our example, you are not considering cover songs. Let's go back to the example. After adding the song titles and their artist names to the hash map instance, it's easy and quick to look up a song's artist by its title and print it. Here, the output from the print line will be Nat King Cole. This is correct. The song, LOVE, is no longer associated with Alvin and the Chipmunks. The entry's artist is now Nat King Cole, because you set the LOVE key to the value of Nat King Cole after you put in the LOVE key with the value of Alvin and the Chipmunks. Hash map instances are extremely fast at looking up values by their key. They use hash algorithms to convert the key into a value that can be indexed and quickly referenced inside the hash map. Every instance used as a key must provide its hashed key to the hash map. The built-in data types, such as java.lang.string and int, all have built-in hashcode value algorithms. It's also possible to create custom hash algorithms for the classes you create, which will be covered later in the course. In this video, you learned that a hash map stores values in key value pairs and ensures that keys are unique. A hash map is used to quickly and efficiently look up values by their keys. It is an excellent addition to your software development toolkit when dealing with large amounts of data. Imagine that the music application you're building needs to track thousands of songs. While you've mastered adding and retrieving key value pairs using a hash map, there's much more you can do with it to enhance your application. Let's explore how. In this video, you will learn about some of the basic operations in hash maps, including replacing values, checking for the existence of keys, getting the number of key value pairs, clearing the hash map, and checking if the hash map is empty. Let's return to the sample of songs and artists from earlier. Song titles such as Satisfaction and their corresponding artists such as the Rolling Stones are stored in the hash map. Remember that song titles are unique to each song, meaning they are an identifier that can be used as a key. The name of the artist or band is the value. To demonstrate some basic operations of hash maps, a Java application called SongMap imports the hash map type and then creates an instance of a hash map that uses string types for both the keys and the values. It then uses the put method to add a few song titles and artists to the hash map instance. This should be familiar to you from the previous video. If you run the SongMap application, the output will look like this. Inside the curly braces, each song title and its corresponding artist's name. This is the default format when printing a hash map. As you learned, if the put method adds a key value pair to an existing key, the hash map will update the value. Let's update the song title Yesterday to a new artist. The replaced value is returned if the put method updates an existing value. Running the program produces the following output. Initially, the hash map contains the key Yesterday with the value Ray Charles. When the put method updates the value to the Beatles, it returns the previous value Ray Charles. Now the map shows that the Yesterday song title has the value of the Beatles. Returning the value previously mapped to a key can be useful when you are unsure what the original value was or need to do something with it, such as adding it to a different hash map or logging the update. If you use the put method with a key that isn't in the hash map, it will simply add it as a new key value pair and return null. The return value is null when the put value adds a new key value pair. So, if Yesterday wasn't already in the hash map, a new entry would be added, and the put method would return null. Another method that behaves similarly to the put method is the replace method. Let's change the put method call with the replace method call and see what happens. Running the program with the replace method call results in the same output as when the put method call was used. The method returns the value, Ray Charles, and replaces it with the Beatles for the key, yesterday. However, the replace method behaves differently from the put method if it's called with a key that doesn't already exist in HashMap. The following attempts to replace the value mapped to the LOVE song title with the artist Nat King Cole. Running the program results in the following output. In this case, the value returned is null because the key, LOVE, doesn't exist in the hash map. If the key doesn't already exist in the hash map, the replace method doesn't modify the hash map. The map has the same contents before and after the call for the replacement method. The replace method is useful when you do not want to add a new key value pair if the key isn't already in the hash map. It will only update a value if the key is already present. You can check for the presence of a key using the contains key method. The contains key method returns a Boolean value. To demonstrate, the program tests for a key you know is in the hash map and then checks for a key you know is not in the hash map. Running the program results in the following output. True for testing for jump, but false when testing for LOVE. Knowing the number of elements in a hash map is often helpful. For example, you could display the total number of songs in the music application to the user. The size method can provide this information. The size method returns an int value equal to the number of key value pairs in the hash map. The print statement displays the size. The clear method removes all the contents from the hash map. If you call the clear method and then print the contents of the hash map, you get empty curly braces, signaling that the hash map is empty. Finally, you can use the isEmpty method to test if the hash map contains any elements. If the hash map is empty, the method returns true. If it has at least one key value pair, it returns false. In this case, the output is true because you called the clear method and emptied the hash map before calling the isEmpty method. In summary, the hash map is a powerful key value collection that enables lightning-fast access to data using unique key identifiers. Beyond basic operations like adding and updating entries, it offers advanced features to conditionally replace entries, check key presence, count elements, clear all entries, and verify if the map is empty. As a staple tool for Java developers, mastering hash maps will significantly enhance your ability to build efficient and dynamic applications, such as developing a music application that can hold large datasets. When managing large datasets, the data structure you choose can make or break your application's efficiency. While HashMap shines in certain situations, it's not always the top choice. In this video, you'll learn how to leverage HashMap by understanding its performance characteristics, common use cases, and trade-offs. A hash map is like a digital dictionary where you store data as key value pairs. You can quickly look up a value if you know its key. For instance, you might store student IDs as keys and their names as values. But if keys or identifiers aren't important, you might be better off using a standard array, array list, or linked list. When you put a key value pair into a hash map, Java uses a hash function to convert the key into an index in its internal array. This enables quick access later. When you call the get method, the hash map hashes the key and goes directly to the corresponding index in its array. The average time to find, insert, or remove a key value pair in a hash map is typically very fast, around 01. This means the time doesn't increase much as more key value pairs are added. However, if many keys hash the same index, operations can slow down, potentially to ON in the worst case, meaning the efficiency of the hash map could be affected by the number of stored pairs. This is rare, but the hash map can slow down when it happens. In order to know when to implement a hash map, you'll need to understand how it uses memory and storage. To operate efficiently, HashMap uses extra memory and stores data in an array. A hash map starts with a capacity of 16, meaning it can initially hold up to 16 key value pairs. Each time a hash map exceeds its current capacity, it automatically doubles in size, requiring additional memory and processing power. With every instance of exceeding the capacity, the size continues to increase. In short, as you add more key value pairs, the array may need to grow, and this resizing consumes additional memory and time. The efficiency in storage a hash map offers means it outperforms other collection types in certain scenarios. To better appreciate its advantages, consider a university's registration system. First, a hash map is ideal for caching frequently accessed data, such as storing student data for quick retrieval in a web application. It's useful for counting occurrences, like the number of students registered for each class, where class codes are keys and student counts are values. HashMap is ideal for tasks like looking up a student's data by student ID. You store IDs as keys and student data objects as values, making lookups very fast. You can group data based on a specific attribute, like grouping students by grade. Now that you know these common use cases, let's explore when a hash map is the best choice for your project. In general, a hash map is great for a number of tasks and project conditions. HashMap is excellent for frequent lookups. First, if you frequently search for data by identifier, such as a student ID, HashMap is an excellent choice due to its fast lookup time. When data volume changes frequently and unpredictably, HashMap handles it well because it resizes as needed. And lastly, HashMap works best when keys are well distributed, meaning only a few keys hash to the same array index. This is difficult to predict, but complex keys are less likely to collide. While HashMap is fast, it comes with trade-offs. Most critically, it uses more memory than other collection types. A hash map requires space for the underlying array and additional space to maintain efficiency as it grows. If memory usage is a concern, consider other data structures like ArrayList or linked list. When selecting a data structure, consider your application's needs and ask, how frequently will I need to search, insert, or delete data? Is minimizing memory usage a priority for this application? Do I need the data to be sorted or evenly distributed in memory? For example, choose a hash map for speed, especially when you need fast searches by identifier and quick insert and delete operations. But consider a tree map, ArrayList, or linked list when sorting data or maintaining sequence, such as sorting students by last name. If conserving memory is important, a standard array, ArrayList, or linked list might be better. It is important to understand that a hash map functions efficiently when the hash values of its keys are evenly distributed across its buckets. Larger and more complex keys tend to generate a wider range of hash values, which helps ensure balanced distribution, reducing the chances of multiple keys being mapped to the same bucket, thus improving performance. A tree map is an option too for sorted data and keeps keys in order, but it is slower for basic operations. Java's hash map is a powerful tool for efficiently storing and retrieving key value pairs. In this video, you've learned how HashMap works, how well it performs, and when it's best to use. In summary, HashMap is ideal for caching, counting frequencies, and quick lookups. However, be mindful of its high memory usage and the potential for slowdowns due to hash collisions. By selecting the right data structure, you can leverage HashMap for efficient, high-performance solutions while managing trade-offs effectively. Picture this. You are developing a university class registration system. One problem that needs to be addressed is the waiting lists for full classes. In this scenario, you have to maintain the order in which students were added to the waiting list, but you also need to be able to find students quickly, regardless of their position on the waiting list. While a hash map is unordered, there is another Java class that you can use to achieve this, the linked hash map. In this video, you will understand what a linked hash map is, and how it's used, specifically how it can maintain the order of entries while providing efficient access to data. Remember that when you iterate through a hash map, the order in which you add the entries and the order they enumerate are unrelated. Hash maps do not order their entries. A linked hash map, on the other hand, maintains the order in which the entries were added. For example, in the registration system, a linked hash map can maintain the order in which students are added to the waiting list. To better understand how the linked hash map provides ordered entries, you can develop an application that adds students to a linked hash map. Then, print out the entries and see if the enumerated order matches the order in which they were added. The first thing you need to do is import the linked hash map type into our program. Like the hash map, the linked hash map is a member of the Java util package. Next, you create a class with a main method as a framework for our example. Once you have accomplished that, you can create the linked hash map. The linked hash map will store students' ID numbers as the keys and their full names as the values. You can add several students to the linked hash map in the order they requested to be added to the waitlist. You can iterate through the linked hash map to see all the students and the order in which they were added to the linked hash map. To do this, add a new static method below the main method that will print out the contents of the linked hash map. You will use this output method frequently. The variable I shows each student's numerical position on the waiting list. The for each loops through each entry in the linked hash map, casting them into the map entry type. It then prints the student's position, ID, and name. Call this method right after you add all the entries to the linked hash map. When you run the application, the output demonstrates that the enumerated items are in the same order as they were added to the linked hash map. The result is that the order in which the entries were added is preserved, with the first entry added being the first one printed. An interesting feature of the linked hash map is that it maintains the position of a key even if you update it with a different value. For example, use the put method to update the value associated with the fourth entry from John Smith to Lydia Apple, as shown here. When you print out the linked hash map, the order is the same, but the name associated with the fourth entry has been changed to Lydia Apple. This default ordering of entries in the linked hash map is called insertion order and is useful when you need to maintain the order in which items were added. The linked hash map supports another ordering system called access order, which will be covered in a future video. The tree map, similar to the linked hash map, can maintain the natural order of a key, meaning that it keeps whatever order might have built into the key. With the tree map, you can also customize the ordering. The tree map will also be covered in a future video. To wrap up, we've seen how the linked hash map can be a powerful tool in our university class registration system, especially for managing waiting lists. By maintaining the insertion order, linked hash map ensures that students are processed in the exact order they join the waitlist, while allowing quick access to any student's information. This balance of order and efficiency is crucial for developing a seamless and effective registration system and any other application that requires maintaining ordered entries with quick access. The fast access offered by hash maps is invaluable for quick data retrieval. But what if they also kept entries in order? That would be useful for scenarios like processing tasks in the order they arrive, or maintaining the sequence of events, like a waiting list. In this video, you'll learn how to manage elements in a linked hash map, including adding, removing, and retrieving entries while preserving their insertion order. Unlike a hash map, where the order of entries is unpredictable, a linked hash map maintains the sequence in which items were added. This feature is crucial when order matters. But just like a hash map, the linked hash map supports essential methods like put, get, and remove. This gives developers efficient data handling with the added benefit of preserving entry order. Let's consider an example. In the waiting list scenario, put is used to add students to a waiting list, and get retrieves their details. The linked hash map also has special methods for retrieving the first and last entries. So, when a spot opens up on the waiting list, it's given to the first person on the list, identified using first entry. The output shows that the lucky student who made the first entry is John Wells. Similarly, last entry returns the last person added to the list. Once John Wells gets into the class, we can remove him from the waitlist using the remove method. The remove method then returns the value of the removed entry, confirming that the action was successful. Nice. Knowing who's first and last is just one possible action. But what about everyone else on the list? With a little code, you'll be able to see who's still on the waiting list. As you can see, John Wells has been removed from the waiting list, but now all the other names are visible too. The linked hash map includes the put first and put last methods, which allow you to place an entry at the beginning or end of the list. However, what may not be obvious is how these methods, along with put, affect existing key value pairs. If the key used in put first or put last doesn't already exist, the entry is simply added to the first or last position. Similarly, if put is used with a new key, the entry is added at the end, just like with put last. However, if put first, or put last are used with an existing key, the location of that key value pair will change, depending on the method used. For example, if you take an existing entry and add it again with put first, it not only updates the value, but also moves that entry to the first position. You can try this with the ID CS9857859, which was originally assigned to John Smith. The output shows that David Bean has replaced John Smith for that student ID and is now at the top of the list. The behavior for put last is similar to the behavior for put first, except the entry moves to the end of the list. The put method works a bit differently. If the key is already present, the value is updated, but the key's position remains unchanged. Let's try this with the key AB4453455, currently linked to David Winston in the third position. If we use put to assign Bob Schmidt to this key, it will update the value but keep the key in the third position. Now Bob Schmidt has replaced David Winston, but the key remains in the third position. Perfect. In this video, you've seen how linked map combines fast access with order preservation, and how key methods like put, get, remove, put first, and put last help you manage and maintain the sequence of your data efficiently. These basic yet crucial techniques equip you to handle complex data management tasks with confidence, ensuring your applications run smoothly and efficiently. Managing data efficiently is key, especially with large datasets. But what if you need to prioritize some key value pairs while discarding those used less often, like a university might in its registration system? In this video, you'll learn how to create an access order linked hash map, where entries are ordered by how often they're accessed, not when they were added. To better discuss the concept of access order, consider a university's registration system. Imagine a class called Student that tracks key details for each student. As students log in, the application loads their information using this class. Having quick access to the student's ID, name, and language helps the system serve the student better when inputting data or reviewing information. It would drain computational resources to keep 40,000 student objects in memory. To manage this, you can implement a custom linked hash map that maintains a limited number of student objects in memory. These objects are used throughout the registration process, accessed with the get method, and updated with the put method as students register and input data. As students log in, the custom linked hash map stores their student objects. When it reaches its maximum capacity, it makes room for new logins, by dropping student objects that haven't been used for a while. This might happen, for example, if students walk away from the registration process or close the app without logging off, which happens a lot more than you think. To save resources, we want to keep only the most active student objects in our custom linked hash map. The rest can be stored in a database or on disk and retrieved as needed. This approach is known as the least recently used, or LRU, caching algorithm. In short, the linked hash map automatically removes the least recently used objects to keep only the most active ones in memory. It's a common strategy to reduce system resource loads, and linked hash map natively supports this algorithm. To use the LRU features of linked hash map, you must extend it and override the remove eldest entry method. This method returns false by default, so the least recently used entries are not removed when new objects are added. You can modify this behavior by creating a custom class that extends linked hash map. Notice that the access order map class extends linked hash map, adding a capacity variable, defining its constructor, and overriding the remove eldest entry method. The access order map constructor calls the linked hash map superconstructor, passing in the capacity parameter while keeping a copy of the value. It also passes a standard load factor, the default setting for balancing memory and performance, and true for the access order parameter. The access order boolean tells the linked hash map to move the most recently accessed student object to the last position, shifting all other student objects toward the first position. The overridden remove eldest entry method checks the map's current size against its capacity. If the size exceeds the capacity, it returns true, removing the first entry. If not, it returns false and nothing is removed. So if you print the contents of access order map after adding 4 student objects, you'll see their order matches the order in which they were added. As expected, Antonio Lopez was added last, so he is in the last position. John Wells, added first, is in the first position as the least recently used object. The order changes as soon as we do anything to the entries in the linked hash map. For example, if you call get on the third entry like this, and then print out the contents again. David Winston, who was in the third position, is now in the last position because it was the most recently used object. If adding a new entry causes the linked hash map to exceed its capacity, the least recently used object, which is in the first position, will be removed. To see this in action, write the following code to add a new student object and then print the linked hash map again. The entry with an ID of 1, John Wells, in the first position was removed as planned, and the new entry with an ID of 5, Alan Cornworth, was added at the end. Perfect. The order has shifted. The linked hash map now reflects the LRU caching algorithm. The most recently used objects are preserved at the end, while the least recently used are ready to be removed from the front. In this video, you've learned how an access order, linked hash map, prioritizes the most frequently used entries while automatically discarding the least used ones. By extending the linked hash map and overriding key methods, you can efficiently manage memory and performance, making this approach ideal for implementing caching mechanisms like LRU caches. Whether managing a registration system or large datasets, access order linked hash map ensures crucial data is always accessible. This maximizes the efficiency and performance of any application you're working on. Imagine a bustling university registration day, where thousands of new and returning students sign up for classes. Your task is to keep all their names in perfect alphabetical order for each subject, no matter the chaos. But here's the challenge. Students register randomly, not alphabetically. So, you need a way to ensure every new registration fits into place alphabetically. Enter the tree map, your tool for turning chaos into order. A tree map works much like a linked hash map, storing key value pairs. But unlike a linked hash map, a tree map automatically sorts these pairs. Your keys will be sorted alphabetically from A to Z if they are student names. Conversely, they'll be sorted from 0 to 9 if the keys are numbers. In other words, string-type keys are ordered alphabetically, while numbers are stored in ascending numerical order, because these are the natural orders of these kinds of key types. Let's explore this in action. You'll create an application that registers students, keeping their names and home countries alphabetically. Start by importing the tree map and map types. The map type is needed to print out the entries in the tree map. Next, create a framework for the application with a class and main method for executing the code. Now you can create an instance of the tree map and add several students and their addresses. Finally, print out the entries in the order provided by the tree map using a static method called printTree. Now, if you run this application, the output will show the students listed alphabetically. Remember that without specifying it, the tree map automatically ordered entries by their key, the name, in ascending alphabetical order. Had the keys been numerical, integers, doubles, etc., the items would have been ordered in numerical ascending order. The Java API defines several temporal types, such as date and time, that support natural ordering. However, most of the Java types you will use, besides strings, numerical values, and temporal types, do not support natural ordering. To account for this, use a pluggable ordering object, called a comparator, for types that do not have a natural order in Java, including those you define yourself. A comparator is any class that implements the Java util comparator interface. This interface has more than 24 methods, but the compare method is what you will focus on now. To demonstrate, here is an implementation of the comparator interface that orders the students by their last names in ascending alphabetical order. The compare method takes two objects that should be compared and returns an integer, which can be a negative number, a 0, or a positive number. If the integer returned by the compare method is negative, the first parameter is less than the second object. For example, 1 is numerically less than 2, and B is alphabetically less than A. If the compare method returns 0, the two objects are somehow equal. 1 equals 1, and A equals A. If it returns a positive number, the first object is, somehow, greater than the second. For example, 3.2 is numerically greater than 3.0, and the word cat is alphabetically greater than bat. The last name comparator compares two objects by their last names. First, it casts the objects passed into the compare method to string types. Then it sends each string to a custom method called lastName. The lastName method simply looks for the last space in the string and returns everything that follows. The underlying assumption is that the space separates the first name from the last name, and everything that follows that space is the last name. It's not perfect, but it works for this example and demonstrates that you can customize your processing when implementing the comparator interface. After the lastName method returns, you can use the lastName string values and the string type's built-in natural ordering to determine whether the last name of the first key is less than, equal to, or greater than the second key. The compareTo method is built into the string type and does the same action as a comparator. It returns a negative number if the calling string appears alphabetically before the parameter string. It returns 0 if both strings are the same. It returns a positive number if the parameter string comes before the calling string alphabetically. Let's test this comparator in action. Create a new instance of the tree map, but this time pass in the lastName comparator in the constructor. Next, add all the key value pairs in the same order you did for the first tree map. When the second tree map is enumerated and printed, the entries are printed alphabetically by last name, not in the natural order of the full name or the order in which they were added. Overall, the tree map provides tremendous advantages when ordering key value pairs, and you can take advantage of custom ordering by creating comparator objects. The tree map isn't just about keeping things in order. It's about putting you in control. You can tailor the sorting to your needs with the right compare method. experiment with your comparator objects, and see how custom ordering can simplify your coding challenges. Imagine effortlessly transforming messy data into neatly ordered structures. Take the plunge, start experimenting, and unlock the full potential of TreeMap. Picture yourself designing a reporting feature for a university's registration office. This tool must provide swift and precise access to student data. How would you ensure that the GPA scores are managed efficiently and accurately? TreeMaps can be an ideal solution for such challenges that involve sorting and retrieving data based on keys. In this lesson, you will learn how to effectively navigate through the elements of a TreeMap, using methods like first key, last key, higher key, and lower key. First, a TreeMap stores key-value pairs in a sorted order. This sorting is based on the key's natural ordering, or by a comparator provided at TreeMap creation time. The inherent ordering allows for efficient retrieval of elements based on their keys. To understand how this is useful in the real world, imagine you are creating a TreeMap that uses students' GPAs as keys and their names as values. For simplicity, assume no two students have the same GPA. The TreeMap does not have a comparator, so it will use the natural ordering of the keys, which in this case are double types. When you run the program, the output prints the students from the lowest GPA to the highest. Great. And the TreeMap automatically orders the key value pairs according to the natural ordering of the double type used as the key. Now imagine you just need to know which student has the lowest GPA. The first key method returns the first, in other words the lowest, key currently in the map. Because of natural ordering, this would also be the lowest GPA. Here, the first key method is used to access this lowest key value. The next line uses the get method to retrieve the value associated with that key, in this case, the student's name. The last two lines print out the results. If you know the types of the keys and the values, you can cast them to their proper types as you access them in the TreeMap. When the types of keys or values are not known or incorrectly cast in a TreeMap, it can limit how the map is used and may lead to runtime errors. Casting the types is not needed in this scenario, but it would be helpful in cases where you need to work more intensely with the keys and values rather than just printing them out. Another way to fetch the first key value pair is using the first entry method. This makes the code look more complicated because you have to deal with the map entry type, but it's also more convenient. The output is the same. We just used first entry instead of first key. Note that all methods here have a map entry counterpart for fetching both key and value. We'll use key methods, but map entry methods are also available. Now let's turn to another useful method, the last key method, which accesses the key with the highest value in the TreeMap. In terms of GPA scores, this method would access the highest GPA according to the natural ordering of the double values. Calling this method is straightforward. Using object allows the variable to hold any type of object, providing flexibility but requiring type checking and casting if you need to use the value in a type-specific way. The output includes the student with the highest GPA was successfully retrieved from the TreeMap. Perfect. To get more specific with our navigation, the higher key method returns the next higher key compared to the key passed in as a parameter. To do this, call the method using one of the existing keys and print the output. Notice that higher key method fetches the next higher key, 3.75, not just any higher key. The higher key method works with any parameter, not just existing keys, as long as the parameter is the same type as the keys in the TreeMap. For example, here we are searching for the next higher GPA above 3.6. In the output, the 3.6 GPA isn't an existing key in the TreeMap, but the higher key method used it to find a GPA that was the next higher GPA. Just as the higher key method finds the next higher key compared to the parameter, the lower key method finds the next lower key in the TreeMap compared to the parameter. If no higher key or lower key exists, the method returns null. This can be used with any parameter of the right type, not just existing keys. When you run the program, the result reveals that 3.5 is the next lower key below 3.6. There are other lower keys in the tree map, such as 3.25 and 3.0, but the next lower key is 3.5. Navigating a tree map is an essential skill for Java developers. The tree map class provides methods to efficiently traverse and manipulate elements based on their keys. Understanding methods like first key, last key, higher key, and lower key allows developers to leverage the tree map's sorted nature for efficient key-based operations. Skills for effectively managing and navigating datasets are valuable for solving real-world challenges, such as developing dynamic reporting features for university registration systems or any application requiring efficient data organization and retrieval. By mastering these methods, you'll ensure your Java applications and solutions are both performant and robust. Java developers use a variety of data structures, each offering unique performance characteristics and specific use cases. Among the most useful advanced data structures in Java, the tree map class stands out for its ability to maintain key-value pairs in sorted order. In this lesson, you'll explore tree map's performance, learn how to handle common use cases, and discover when it's best to use tree map over other data structures, specifically hash maps. So, how exactly does a tree map organize its data so well? A tree map uses what's called a red-black tree approach to organize entries internally. In a tree map, each key-value pair links to two other entries, one with a lower key and one with a higher key. This structure ensures the keys are maintained in sorted order, which is great for efficient data retrieval and maintaining sorted sequences. In the tree, the root is the entry with the key of 10. Keys lower in order are referenced on the left, and the higher keys are on the right. So, for example, 5 is found to the left of 10 because it's a lower value, and 15 is to the right because it's higher. When the entry with the 3 key is added, it's less than 10 and less than 5, so it falls to the left reference of the entry with the 5 key, and so on. This structure is great for ordering any set of keys naturally or by comparator. The tree map continuously works to keep the structure balanced, much like a well-architected pyramid. It aims to minimize the width and height of the tree, ensuring efficient data retrieval and maintaining sorted sequences. This maintenance impacts performance, as the operations of adding, removing, and finding elements all have a time complexity of O log n, where n is the number of elements in the tree map. This is because the tree map doesn't use an underlying array, like a hash map. Instead, it links all its entries together in a pyramid structure. This results in more complexity and more time is required to find, add, and remove key-value pairs than with the hash map. Another key performance characteristic of a tree map relates to iteration. Iterating over the key or values is relatively fast with a tree map because the keys are maintained in sorted order. The tree map maintains extra data. Each entry links to two other entries to ensure the tree remains balanced in a pyramidal shape. This ordered structure facilitates efficient retrieval and is particularly useful for applications requiring ordered data processing, such as range queries and data navigation. However, note that while this memory overhead is generally not significant, it can be a consideration in memory-constrained environments. In terms of use cases for a tree map, two stand out: sort ordering and navigation. When the requirement is to maintain elements in a sorted order, tree map is the go-to choice. For example, an alphabetical list of students. The tree map also provides methods that make it easier to navigate among keys, including the methods first key, last key, lower key, and higher key. For example, finding the lowest or highest GPA among students at a university. Tree map and hash map are suited to different use cases, each offering unique advantages. Let's highlight the key differences to help you make informed decisions on which to use and when. First, the hash map is faster than a tree map because it uses an array internally and indexes entries according to the hash code of their keys. A tree map, on the other hand, links entries together, requiring more work and time to add, remove, and find entries. The hash map also uses less memory than a tree map, because it maintains fewer objects than a tree map. While the differences are negligible with small datasets, they become more important with very large datasets. Crucially, the hash map does not maintain entries in any particular order. When you iterate through a hash map, you cannot predict in what order the key value pairs will be enumerated. A tree map maintains the natural order of the keys, or it can be initialized with a comparator to maintain a custom order. Finally, the navigation capabilities of a tree map are more sophisticated than a hash map. Both the hash map and tree map can fetch a value directly by its key and iterate through the entries, but the tree map can also access entries based on their relative sort order, such as the next highest key, something that the hash map cannot do. To wrap up, the tree map in Java is a powerful data structure that offers efficient sorted key value pair management. Its performance characteristics in adding, removing, and finding key value pairs make it suitable for various use cases where order and consistency are paramount. A tree map does have trade-offs in terms of memory usage and slightly slower operations compared to hash map. However, its ability to maintain order and provide more sophisticated navigation makes it indispensable in scenarios requiring sorted data. In short, choosing between tree map and hash map ultimately depends on your application's specific requirements. For sorted data, tree map is the better choice. For fast access and lower memory usage, hash map is preferable. By understanding these differences, Java developers can make better informed decisions about when to use advanced data structures. This ensures their applications perform optimally and meet the requirements for order and efficiency. Searching for a friend's phone number in an extensive phone book can be done in two ways. You could start from the beginning and scan each name one by one until you find it. While this approach works, it could be time-consuming if your friend's name, such as Sarah, was listed towards the end. A faster way is to skip ahead to the section with names starting with S. This simple analogy reflects how search engines efficiently help to find information in the digital world. Searching algorithms are computing techniques for finding specific data within a larger data set. Searching algorithms are essential in today's digital world, where vast amounts of data are generated every day through activities like sending emails, posting on social media, and using cloud services. Finding a single file amid this sea of information, like locating one file on your computer without the search function, would be overwhelmingly time-consuming without efficient searching algorithms. Searching algorithms optimize this process by quickly and accurately identifying the required information, saving time and computer resources, such as storage, processing power, and memory. Several types of searching algorithms exist, such as linear search, binary search, jump search, exponential search, and interpolation search. Among these, linear and binary search stand out due to their simplicity and widespread use. In this video, you will learn about these two crucial searching algorithms. Let's get started. The linear search is the simplest type of searching algorithm. It's like starting at the beginning of the phone book and checking each name one by one until you find Sarah. In a linear search, the computer processes the data from beginning to end, comparing each item to the target item. For example, if you were searching for a number in a list of unsorted phone numbers, the linear search would start at the first number, compare it to your target, and move on to the next one if it's not a match. This process repeats until the number is found or the list ends. Linear search works best when dealing with small, unsorted data sets, or when data is arranged in a sequence that doesn't follow any order. It's often used when the dataset is so small that sorting it or using complex algorithms isn't worth the overhead. It's also ideal when searching for specific items in a list, where the position of the item isn't known, like finding a name in an unordered contact list. Some of its advantages include being easy to implement and understand, working on any data structure, whether sorted or unsorted, and not requiring pre-processing or sorting, making it suitable for immediate searches. Its disadvantages include being slow on large datasets because it checks every element individually, and being inefficient with the time complexity of O of n, meaning the search time grows linearly with data size. In contrast, binary search is much faster, but requires sorting the data. Using the phone book analogy, it's like flipping directly to the section with names starting with S. Instead of checking each name one by one, you start in the middle of the book, roughly at the midpoint of the book based on the first alphabet of the name, and determine whether the name you're searching for comes before or after that midpoint. This way, you can eliminate half of the remaining names and focus on the relevant section. If Sarah's name is after the midpoint, you can immediately rule out the first half of the book from your search. You then repeat this process with the remaining half, selecting a new midpoint and deciding which half to search next. This method significantly reduces the number of comparisons needed to find the target by halving the search space at each step. The binary search is designed for sorted datasets. It's efficient in scenarios where data is already ordered or can be pre-sorted, like finding a word in a dictionary or looking up a number in a phone book. It's commonly used in algorithms where speed and large datasets are critical. A binary search is much faster than a linear search. While a linear search looks at every element one by one, a binary search has a time complexity of O, of log n, which means it repeatedly divides the dataset in half, narrowing down the search quickly. When used on sorted data, a binary search can narrow the target data in just a few steps, no matter how big the dataset is. However, there are some limitations to consider. First, the data must be sorted beforehand. If it isn't already sorted, that adds an extra step, slowing things down. Second, binary search only works with datasets that allow direct access, like arrays. It can't be used on unsorted or dynamically linked data structures. Understanding the fundamentals of searching algorithms, such as linear and binary search, can provide valuable insights into how computers operate behind the scenes to extract information quickly and efficiently. While linear search works well for small or unsorted data, binary search is the go-to strategy for efficiently handling large, sorted datasets. So, the next time you search for something on your computer or online, remember a well-designed algorithm is working behind the scenes to help you find exactly what you need as quickly as possible. Imagine this. You're at a garage sale with a table full of books, toys, clothes, and other goods. You're looking for a specific book to read. However, the objects on the table are not arranged in a particular order. How would you go about finding the book? The most basic technique is to begin at one end of the table and review each item individually until you discover the book you're looking for. This strategy, albeit simple, is precisely how a linear search works. A linear search is one of the most fundamental techniques for finding an item in a list or collection of data. The term linear refers to the fact that the search process proceeds in a straight line from the beginning to the end of the list. This approach doesn't require the list to be sorted and works with any type of data, such as numbers, words, and even objects. Let's break down the linear search algorithm step by step. First, the search starts at the beginning of the list. Then, the algorithm compares the current item in the list to the target value, the item you're searching for. If the current item matches the target value, the search is complete and the position of the item is returned. If the current item does not match the target value, the search moves on to the next item in the list. The process is repeated, comparing each item with the target value. Finally, if the search reaches the end of the list without finding the target value, it concludes that the item doesn't exist in the list. Let's demonstrate linear search using a Java example. You'll define an unsorted integer array of 6 numbers, specifically 3, 8, 1, 5, 9, and 2. The target number is 5. You'll write a class called linear search number example with a linear search method. This method takes an integer array and a target value to search for the target's index in the array. The target integer is searched inside the array, and its index is returned. The linear search method is responsible for finding a target number in an array. The integer array represents the array of numbers you want to search, while the target integer is the number you are trying to find in the array. The for loop goes through each element in the array ARR. At each step, it checks if the current number, ARRI, equals the target number. If it finds the target, it immediately returns the index I, where the target is located in the array. If the loop finishes and the target isn't found, the method returns -1 to indicate that the number isn't in the array. Now back to the main method with an integer array of numbers and the target value. These two variables will be passed as arguments to the linear search method. Inside the method, define the unsorted array of numbers. The array numbers hold 6 different numbers. They are not in any particular order. Next, you define the target number that you want to search for. In this case, you're searching for the number 5 in the array. Then the program calls the linear search method to search for the target. This method returns the index of the target if it finds the number, or -1 if the number is not found. After the search, the result is stored in the variable result, and the program checks whether the target was found. If the result is -1, the program prints number not found. If the result is any other number, it prints the message number found at index, followed by the index where the target number was located in the array. Behind the scenes, the linear search algorithm would start by comparing 3 to 5. Since 3 is not equal to 5, it would move to the following number. Then it compares 8 with 5. Again, they don't match, so it moves on. Next in the list, the linear search compares 1 with 5. There is still no match, so again it moves on. Now it compares the next number, 5, with the target value, 5. This time they match. The search is successful and the algorithm stops. The program's output now says number found at index 3. Let's summarize what you've just learned about a linear search. The dataset doesn't need sorting for the algorithm to work. The algorithm loops through the array by iterating over each element, comparing the current element with the target value. If a match is found, it returns the element's index. If it isn't found, the loop completes without finding the target and returns -1. In your example, if the target number of 5 isn't found, it indicates that the number isn't present. The time complexity of the linear search is O(n, O(n, O(n), where n is the number of elements in the array. So, when should you use a linear search? Use it when you have short lists or unsorted data. While it may not be the fastest approach, its simplicity makes it an excellent choice when ease of implementation takes precedence over speed. While a linear search is simple and easy to implement, it does have its drawbacks, especially with larger datasets. It is inefficient with large lists because it checks every item. If the list is long and the target item is near the end or not present, the search can take a lot of time. It's also not suitable for sorted data. If the data is sorted, use other search algorithms, like the binary search algorithm. The linear search, while basic, is a valuable tool for developers. It's easy to understand and implement, making it a great starting point for understanding search algorithms. By now you're familiar with linear search and know it isn't the most suitable algorithm for long lists or large datasets. In this video, you'll explore the concept of temporal or time complexity, which refers to how the algorithm's running timescales with the size of the input data. In simpler terms, it measures how much longer a task will take as the task itself gets bigger. The time required for a linear search increases directly with the length of the list, as indicated by the formula O of n. The O means order of, and the n tells you how many items are in the list. For example, if the list contains 10 items, it might take up to 10 comparisons to find the desired item. Similarly, with 1,000 items, the search could take as many as 1,000 comparisons. To demonstrate how time complexity works in a linear search, write a Java class, linear search time complexity example. It will have a linear search method. It performs the search and counts how many comparisons are made. The method will return the maximum number of comparisons to find the target inside the array. Its parameters contain an int ARR, the array that is searched, and an int target, the number you're trying to find. Let's understand how this works. The int comparison equals 0 semicolon indicates the variable that keeps track of how many comparisons are made. The for loop goes through each element in the array. For each element, the comparisons ++ increases the comparison count by 1. The program checks if the current element equals the target number. If it finds the target, it returns the number of comparisons made so far. If the loop finishes and doesn't find the target, the method returns the total number of comparisons made during the search. Now, write the main method to set everything up. The program performs several actions. First, it creates 3 arrays of different sizes. The small array contains 10 numbers already filled with values. The medium array has 100 spaces that need numbers filled in. There's also a large array, 1,000 spaces, that also need filling. The program fills the medium and large arrays with values from 1 to 100 and 1 to 1,000 respectively. Each array element is filled with numbers in increasing order in these loops. The first loop fills the medium array, and the second loop fills the large array. The second action requires the program to set the target value being searched. In this case, it's 50, which is the number the program will search for in all 3 arrays. Finally, the program then calls the linear search method 3 times, once for each array, and prints how many comparisons it took to either find the target or finish searching the entire array. Let's break down what happens in each array. Suppose you have a list of 10 elements. In this example, the last number in the array is 10. So for the program to find the target value of 10, it would first check all 9 elements before finally finding the target at the 10th position. Now imagine a list with 100 elements. If you're searching for the number 100 at the end of the list, the linear search will check all 99 elements before it reaches the 100th one. Finally, consider a list with 1,000 elements. If you're searching for the number 1,000, the linear search will go through all 999 preceding elements before finding the target. For each search, the program prints out the number of comparisons needed to find the target or finish searching the entire array. The reason linear search is O of n is because, in the worst case, you might have to check every element in the list to find the one you're looking for, or to confirm that it's not in the list. This is a direct relationship. If the number of elements doubles, the maximum number of comparisons also doubles. Linear search is simple to construct and works well with small or unsorted lists. But because it has an O of n time complexity, the time it takes to search increases as the list grows. If you anticipate working with massive datasets, understanding the time complexity may lead you to investigate more efficient search algorithms, such as binary search, which has a time complexity of O of log n and scales considerably better with larger datasets. Knowing which algorithm to use and when comes with experience. You will soon learn which to use when given a scenario. Keep learning and growing your skills. Repeatedly finding specific data in large datasets is a common challenge. When those datasets are sorted, efficiency-minded developers rely on binary search algorithms to get the job done. In this video, you'll learn how binary search's divide and conquer approach makes searching sorted data a breeze. Binary search is an efficient algorithm to quickly find a target value in a sorted list or array. It does this by repeatedly halving the search space. If a target is smaller than the middle value, the search space is halved again. The process repeats, halving the search space until the target is found or the list is empty. If the target value is found, the algorithm returns its position in the list. If the search interval is exhausted and the target isn't found, the algorithm concludes the target is not in the list. Let's turn to Java now and see how binary search works with an example. For this demonstration, we'll create a Java class called BinarySearchDemo. It has 2 key parts, the main method, which starts the program, and the binary search method, which performs the search. The binary search method performs the actual binary search. The parameters here are int array r, the sorted array to search, and int target for the number to find. The method divides and eliminates sections of the array. The method uses 2 pointers. Left points to the start of the array and right to the end. A while loop continues checking the middle element and updating the pointers until the target is found or the search ends. The middle or mid index is calculated. If the middle element equals the target, the method returns the index mid. If not, it updates the left or right pointer and continues the search. If the target is greater than the value at the middle index, the program eliminates the left half and updates the left pointer to mid plus 1, continuing the search in the right half. If the target is smaller than the middle element, the program eliminates the right half and updates the right pointer to mid minus 1, continuing in the left half. If the while loop finishes without finding the target, meaning left has become greater than right, the method returns minus 1, indicating that the target number is not in the array. Next, write the main method that includes the array and target number. These 2 values are passed to the binary search method to find the target's index or determine it isn't in the array. Here is where you set up the array and the target number you want to search for. First, the array. This is a sorted array of integers from 2 to 99, meaning the numbers are arranged in increasing order. The fact that the array is sorted is important because binary search only works on sorted data. Let's say the target number is 23. The program calls the binary search method and passes the numbers array and the target number as arguments. The result will be the index position of the target in the array, or minus 1 if the target is not found. If the binary search method returns minus 1, it means the target number was not found in the array, and the program prints number not found. Otherwise, the program prints the index where the target number was found. What the binary search algorithm is doing here is quite simple. With the array and target number in mind, it's starting with the middle element, 45. And since 23 is smaller than 45, it focuses on the lower half of the array. Next, the middle element of the sublist is 7. Since 23 is greater than 7, focus on the upper half, so the third and fourth positions, 10 and 23. Finally, the search starts its next pass with the closest middle element, which is our target number, 23, at index 4. This approach to search isn't for unsorted lists, but for large sorted datasets, it's the most efficient. The time complexity of binary search is logarithmic, meaning the search time increases at a much slower rate compared to the size of the dataset. In other words, even as the dataset grows, binary search dramatically reduces the number of comparisons needed to find the target. For large-scale and high-performance applications, it's perfect. While binary search is ideal for large, sorted datasets, not all data is sorted or extensive. In such cases, a linear search becomes the more practical option for unsorted data. However, if sorting the data first is feasible, binary search can once again be the more efficient choice. Additionally, when working with more complex data structures, implementing binary search becomes significantly more challenging compared to the simplicity of linear search. For large sorted datasets, where searches need to be performed repeatedly and efficiently, binary search is the ideal choice. By halving the search space with each step, it significantly reduces the number of comparisons, making the process both faster and more effective. Binary search plays a key role in solving real-world challenges, from optimizing search engines to enhancing database queries. And now it's a valuable tool in your coding toolkit. I'm thinking of a number between 1 and 100. If I tell you whether your guess is higher or lower, what's the fastest way to find it? You could count up from 1 or down from 100, or guess randomly. But the most efficient way is to start in the middle, 50, and halve the options with each guess. This is how binary search works, quickly narrowing down possibilities. In this video, you'll learn how binary search uses this strategy and why its time complexity, O of log n, makes it so efficient for larger datasets. Time complexity helps explain how an algorithm's runtime changes as the input size grows. For binary search, the time complexity is O of log n, meaning that as the list gets larger, the time required to find an item increases much more slowly, following a logarithmic rate. Let's break down what O of log n means, with examples that show how binary search stays efficient as datasets grow. We'll use a Java class called binary search complexity, which is a method to calculate max comparisons. This method takes an integer and returns the O of log n value for that input. This method calculates the maximum number of comparisons binary search requires, depending on the size of the array n. In binary searches like this, each comparison eliminates half of the array. The number of comparisons depends on how many times the array can be halved. The formula mat.log of n divided by mat.log of 2 gives the base 2 logarithm, which shows how often you can split the array. For example, if the array has 8 elements, you can halve it 3 times. So, in the worst case, it would take 3 comparisons to find your target. Next, we'll write the main method, which creates an array with values 10, 100, and 1000. Each value is passed to the calculate max comparisons method, and the results are looped through. The main method sets up an array called sizes that contains the values 10, 100, and 1000. For each size, the number of comparisons required by binary search is calculated and the results are displayed. This for each loop goes through the array sizes 10, 100, and 1000 and calls calculate max comparisons for each. It will print the result for each value. For an array of size 10, binary search might require up to 4 comparisons. For size 100, it could take 7 comparisons, and for size 1000, up to 10 comparisons. Let's look at lists with 10, 100, and 1000 elements to further illustrate how binary search affects time complexity in practice. Take a sorted list with 10 elements. In the first comparison, check the middle element at the 5th position. Depending on whether the target is smaller or larger, look at the middle of the remaining halves. So, either the 2nd or 8th position. Repeat this process, halving the list with each step until you find the target. In the worst case, how many steps will it take? The time complexity is O of log 10, or approximately 3.32. This means binary search will require about 3.32 steps to find the target in a list of 10 elements. Now consider a sorted list with 100 elements. Binary search will use the same method, but the number of comparisons, or passes, increases slightly because the list is larger. In the first comparison, check the middle element, the 50th position. Depending on the target value, check the middle of the remaining half, either the 25th or 75th position. Continue halving the list with each step until you find the target. The time complexity for this process is O of log 100, approximately O 6.64. So the worst case here will take 7 comparisons. What about a list that has 10 times as many elements? Once again, binary search keeps halving the list until it pinpoints the target value with minimal comparisons. With 1000 elements, the worst case is closer to 10 comparisons. Looking at lists of 10, 100, and 1000 elements shows how binary search scales with larger datasets. The magic of O of log n is that even as the list size grows dramatically, the number of comparisons increases very slowly. This makes binary search incredibly efficient, especially for large datasets. In this video, you learned how binary search's method of halving the search space drastically reduces the steps needed to find an element. The larger and more sorted the list, the more time efficient binary search becomes. Oh, and the number I chose at the beginning? 42. The way a dataset is organized, whether sorted or unsorted, can drastically change how efficiently we can search through it. This is where the choice between linear search and binary search comes into play. In this video, we'll compare the performance of linear and binary search on sorted and unsorted data and how the size of a dataset could influence your decision. Let's start with unsorted data, where the items are in no particular order, like randomly arranged books on a shelf. In this case, linear search is the only option. Why? Without any indexing, binary search has nothing to guide it. There's no way to divide the data in half, so each item must be checked one by one. In practice, the most effective choice would be a program like this, that starts with, say, a class called linear search books. Inside it, we have the linear search method and the main method. String books is the array of book titles you're searching through, and string target is the book title you're trying to find. The program uses a for loop to check each book in the array. It compares the current title with the target using the equals ignore case method, which ignores case differences, like whether Moby Dick starts with an upper or lowercase letter. If the target is found, the method returns its index in the array. If not, it returns -1, indicating the book wasn't found. The method will have a string array of books and a string target set to Moby Dick. Both will be passed as arguments to the linear search method. The program starts by creating an array of book titles, like a list of books on a shelf. It then searches through this list to find a specific one. If the target book is Moby Dick, it passes it to the linear search method. This line calls the linear search method passing the array and target title. It returns the book's index if found, or a -1 if it isn't. For unsorted data, linear search checks each item one by one. It's the default choice for smaller lists, but what about larger unsorted lists? Even with hundreds of unsorted books, linear search is the better option since binary search requires sorting. While binary search can start with unsorted data, linear search becomes inefficient with sorted data. To see binary search in action, let's switch to an alphabetically organized list of books. A binary search of sorted data like this might have a Java class called binary search books. Inside the class, the binary search method takes 2 arguments. Books is the sorted array of book titles, and target is the name of the book being searched for, in this case, Tolkien's classic The Hobbit. Using binary search, the algorithm starts by checking the middle of the list and then determines if The Hobbit is in the first or second half. It continues halving the list until it finds the target or confirms it's not there. To help you choose the right algorithm, let's summarize the best use cases for each. In general, for unsorted lists, linear search is the clear best option, since binary search requires the data to be sorted. But if the data is already sorted or can be sorted first, binary search is much faster. However, the size of the dataset does add some nuance to the choice. So, for small, unsorted datasets, like a few randomly arranged books, linear search is simple and effective. For large, unsorted datasets, linear search can still be used, but sorting the list first could save significant time on repeated lookups. That's because, for sorted lists, binary search is the clearer choice for efficiency. Although, if the dataset is very small, like an unsorted shopping list of 10 items, linear search may still be simpler and shouldn't be completely ruled out. Finally, for large sorted datasets, binary search is the clear winner. Its method of halving the dataset with each step drastically reduces search time and makes it the most efficient choice. In this video, you've seen a comparison of linear and binary search, focusing on their efficiency in different scenarios. By understanding the dataset size and whether it's sorted or unsorted, you can make better decisions about which algorithm to use for optimal performance. Happy searching! Think about your workspace after a long day. You might have documents, stationery, or other items scattered around. To quickly locate what you need, it's much easier when everything is organized and in its proper place, right? While sorting algorithms can't organize your physical workspace, they can perform a similar function for data. They streamline the process of finding and using necessary information quickly, which is particularly valuable for organizations developing efficient applications. Sorting algorithms act as a set of instructions that organize information in a precise and efficient order. When data is sorted, whether it's numbers, words, or objects, It is arranged in a sequence, such as from smallest to largest or alphabetically. This is important because sorted data is easier to manage, search, and analyze. In this video, you will learn how sorting works, how it helps solve problems more efficiently, and how it applies to everyday life and computing. Sorting is a fundamental concept because it helps in organizing information. This is extremely valuable because data needs to be accessed and used effectively. Let's imagine a few scenarios where sorting makes life easier. Take a library, for example. Books are typically organized by the author's last name, genre, or title, making it easy to find what you're looking for. If the books were placed randomly on the shelves, finding a specific one would take much longer, leading to less effective learning. Your phone's contact list is another great example. Typically, contacts are sorted alphabetically, making it easy to scroll and find the person you want to call or text. Now, if the contacts were in a random order, locating a specific name would be frustrating and time-consuming. And if you've enjoyed a seamless online shopping experience, you can thank sorting algorithms. They allow you to sort items by price, customer ratings, or popularity, helping you find the products that best suit your needs. For example, if you're searching for the most affordable option, you can easily sort items from lowest to highest price. As a final example, educators and administrators often sort students' grades from highest to lowest. This makes it easy to review individual performance relative to others and identify trends across the class. Sorting isn't just about convenience, it's about efficiency. In computers, sorting is crucial because it makes searching and organizing data much faster. If you have a list of thousands of names and you need to find one specific name, a sorted list allows the computer to find it quickly without having to check every single name. That's time-saving and valuable. But how do they work exactly? Simply put, sorting algorithms are the step-by-step methods computers use to organize data. Once organized, the data can be accessed or edited quickly and easily. Each algorithm uses a unique technique for sorting, so let's look at some of the most popular ones to understand how they work. For example, bubble sort is one of the simplest sorting algorithms. Imagine you want to sort a deck of playing cards based on the number of the card. A bubble sort algorithm starts by comparing the first two cards. If the first card is larger than the second, it swaps and reorders them. It then moves to the next pair. This process is repeated until all the cards are arranged from smallest to largest. And as it continues with new entries, smaller cards move or bubble to their place in the order. Bubble sort algorithms are used in applications where simplicity and ease of implementation are essential. Their ease of understanding and implementation makes them particularly useful for small datasets or when the dataset is nearly sorted. Another key sorting method is selection sort. It works in sequence by finding the smallest number in a list and moving it to the front. Then it looks for the next smallest number and places it next in line. A selection sorting algorithm starts by picking out the card with the lowest value and moving it to the leftmost position. Then it looks for the next lowest card and places it right after the first one. The process continues until all the cards are arranged from lowest to highest value. Selection sort algorithms are ideal for situations where memory usage is a concern because they minimize the number of swaps. They're particularly useful in scenarios where the dataset is relatively small or where simplicity and predictability in performance are more important than speed. Another useful method is the insertion sort, which organizes data by gradually building a sorted list, inserting each new element into its correct position. If the algorithm starts with one entry and then another comes along, insertion sort places the new entry in its correct position relative to the first. It keeps adding incoming entries one by one, placing each in the right spot until your list is fully organized. With insertion sort, the algorithm takes each value or number from an unsorted list and inserts it into its proper place within a growing ordered list. This process is repeated until the entire list is sorted. Insertion sort algorithms are particularly effective for small or partially sorted datasets. Its simplicity and efficiency make it ideal for real-time applications with limited computational resources, such as embedded systems or manual data entry. Apart from bubble, selection, and insertion sorts, there are many more sorting algorithms worth experimenting with, each with their own strengths and unique applications. The bucket sort groups elements into buckets before sorting. Merge sort divides the list and merges the sorted parts. Radix sort processes numbers by each digit, useful for sorting large numbers or data with a significant range of values. And quick sort is known for its efficiency in partitioning and sorting segments. Sorting algorithms are widely used in real-world applications, playing a crucial role in organizing and processing data across various fields. From social media fields that sort content by recency, or engagement to music streaming services like Spotify that help you discover your next favorite song, these algorithms are integral to our daily digital experiences. Whether it's sorting names, numbers, products, or posts, these algorithms are at the core of many everyday tasks and computer processes. In this video, you learned how key sorting algorithms work, why they're efficient, and how crucial they are to solving real-world challenges. If you understand sorting, you can better grasp how computers solve problems and organize information. This gives you the critical insight to optimize data processing and improve decision-making in any application you choose to develop. You walk into a library and find all the books on a shelf in disarray, some tall and some short, randomly placed. You've been asked to organize them by height, from the shortest to the tallest. Arranging these books neatly not only makes the shelf look tidy, but also makes it easier to find books in the future. In this video, you will learn how to use the bubble sort method to sort items effectively, just like organizing books in a library. Looking at the shelf, you notice the books are in random order. You aim to arrange them so the shortest book is on the left side of the shelf and the tallest book is on the right. This task is similar to sorting data. You will use the bubble sort method, a straightforward approach perfect for small data sets. You begin by comparing the first two books. If the first book is taller than the second, swap their positions, placing the shorter one on the left. Then, compare the second book with the third. If no swap is needed, you will move to the next pair. Keep swapping until you reach the last element. This is known as the first pass. By this first pass, the tallest book will have bubbled up to the end of the row. This mirrors how bubble sort works in programming, iteratively comparing and swapping items to sort a list. With the tallest book in the correct position, repeat the process for the remaining books, known as a pass, ignoring the last one because it's already in its proper spot. You start again from the first book, comparing and swapping if needed. With each pass, the next tallest book moves to its correct position. This process gradually sorts all the books until the shortest is on the far left and the tallest on the far right. You continue repeating the sorting process, each time considering one less book. Eventually, no more swaps are needed, and the books are perfectly sorted from shortest to tallest. So what reflections can you draw from this example? The bubble sort algorithm made the task simple. It required no complex thinking, only comparing and swapping as needed. While it may take longer with more books, bubble sorting is easy to implement for small data collections. Now let's take this into Java and translate the sorting method into code. First, create the main class to start coding. Define an array of integers representing the height of each book in centimeters. Next, the modularity of the code can be enhanced by segregating the frequently used methods. For instance, you'll print the array twice, that is, before and after the sorting. Writing a dedicated method that handles printing the array elements is better, which you can call from the main method function whenever needed. Now you need to call this method to print the array from the main method. This is where the magic of sorting happens. You have to write a separate method to execute the sorting, which is as follows. Name the method as bubble sort and pass on the array. Then call the method from the main method. Now that you have sorted the array, you need to print and check if the array element has been sorted. Here you again need to call the print height method to print the sorted array from the main method. Once you run your program, you'll have the following output, which lists the books in height from shortest at 12 centimeters to tallest at 15 centimeters. Great job! You now know how to use the bubble sort method in Java, which allows smaller elements to bubble up to the correct position through repeated comparisons and swaps. While it's simple and easy to understand, you also discovered that it might not be the most efficient choice for larger datasets. However, it's a great way to get started with sorting algorithms. It provides valuable insights into how sorting works and can be applied in everyday situations like organizing a bookshelf. Tony invited his friends over for a card game. He was dealt a hand of shuffled cards and wants to sort them in ascending order, from the lowest to the highest value. You can sort cards based on the card value or the suit. Tony decides to sort the cards based on the card or number value. Therefore, the number 2 is ranked the lowest and 10 is the highest. A card with the lowest value is 2 and an 8 has the highest value. Can you write a Java program to help Tony sort his cards? In this video, you'll learn how to apply the insertion sort algorithm, simulating how people arrange cards based on card number ranking. The pack of cards only contains the number of cards. First, let's view Tony's initial hand. He has 5 cards, 7 of spades, 3 of diamonds, 10 of clubs, 5 of hearts, and 2 of spades. Sorting the cards by hand requires Tony to pick up a card and place it in the correct position relative to the first card on the left. He will continue this process until all the cards are sorted. Tony starts by considering the first card, the 7 of spades. Since it's the only card, it's already sorted, so no action is needed. The second card is the 3 of diamonds, which is smaller than the 7 of spades. Tony moves the 3 of diamonds to the left of the 7 of spades. His hand is now 3 of diamonds, 7 of spades, 10 of clubs, 5 of hearts, and 2 of spades. The third card is the 10 of clubs, ranked higher than the 7 of spades. Therefore, the card is in the correct position and no sorting is needed. The fourth card is the 5 of hearts. 5 is smaller than 10 and 7 but greater than 3. Therefore, Tony inserts the 5 of hearts between the 3 of diamonds and the 7 of spades. The last card is the 2 of spades. 2 is smaller than 3 and Tony moves the card to the left of the 3 of diamonds. His hand is now sorted from lowest to highest, as the 2 of spades, 3 of diamonds, 5 of hearts, 7 of spades, and 10 of clubs. How does this relate to a Java program? The insertion sort algorithm can simulate the sorting of the cards. Navigate to IntelliJ to explore the insertion sort algorithm in 4 steps. Step 1. You have to create the main class and define an array of integers to store the numbers on the cards. Call the printArray method to display the initial array. You can then compare the before and after sort outputs. The insertion sort method will sort the card values in ascending order. Insert another printArray to view the sorted cards. Step 2. Insert a printArray method consisting of a for loop to iterate over each element in the cards array. The cards variable represents each card value during each iteration. The print method will indicate each card value followed by a space for readability. Outside the for loop, insert a print line statement to view the output on a new line. Step 3. Insert another method and call it Insertion Sort. This method has a for loop that starts from the second element, index 1, and iterates through each element in the array. The purpose of this loop is to pick each card one by one and place it in its correct position relative to the already sorted part of the array. The current card variable stores the value of the current element that needs to be placed in the correct position. Next, insert a while loop as an inner loop. This loop checks if the current element is smaller than the elements in the sorted part of the array from the left side. If so, it shifts the larger elements one position to the right to make space for current card. Therefore, cards counter 2 plus 1 equals cards counter 2, indicates the larger elements are shifted from one position to the right. The counter 2 indicates the decrementing counter and checks the next element on the left. After finding the correct position, the current card is inserted into its appropriate position within the sorted portion of the array. Step 4. Let's view the output. Java sorted the cards just like Tony did. In this video, you learned that the insertion sort method simulated how Tony sorted his cards by placing each new item in the correct position relative to the other cards. Although insertion sort might not be the fastest algorithm for large datasets, it is highly effective and easy to understand for smaller or nearly sorted lists, making it a perfect choice for Tony's task of organizing his hand of cards. Have you played a game where you have to sort items based on size, color, or value? Many games advertise that sorting items can increase your IQ, as it keeps your brain active. Ashley has 5 coins of different sizes and wants to arrange them from smallest to largest. The diameters of the coins are 25, 15, 30, 20, and 10. Can you help Ashley write a Java program that can sort the coins? In this video, you'll learn how to apply the selection sort algorithm, simulating how people arrange coins based on size. First, let's look at how Ashley will sort the coins by hand. She randomly places the coins on a table. The order, based on diameter in millimeters, is 25, 15, 30, 20, and 10. Ashley picks up the smallest coin, the 10 millimeters, and swaps it with the first coin, the 25 millimeter. The order of coins is now 10, 15, 30, 20, and 25. The smallest coin is in the correct position. Next, she looks at the remaining coins and selects the 15 millimeter one as the smallest. Ashley notices that the coin is in the correct position, so swapping coins is unnecessary. The last 3 coins are 30, 20, and 25. Ashley selects the 20 millimeter coin and swaps it with the 30 millimeter coin. So the order of the coins is now 10, 15, 20, 30, and 25. Lastly, she swaps the 30 millimeter with the 25 millimeter. The order of the coins is now 10, 15, 20, 25, and 30. Ashley has sorted the coins from smallest to largest based on their diameter. How does this relate to a Java program? You can use the selection sort algorithm to simulate the sorting of the coins. The algorithm will split the list into 2 groups, a sorted group to the left and an unsorted group to the right. Similarly to what Ashley did, the algorithm will take the smallest size from the unsorted group and place it in the sorted group. When all the coins are sorted, the algorithm will stop. Navigate to IntelliJ to explore the selection sort algorithm in 4 steps. Step 1. You have to create the main class and define an array of integers to store the size of the coins in millimeter. Call the printArray method to display the initial array. You can then compare the before and after sort outputs. The selection sort method will sort the coin sizes in ascending order. Insert another printArray to view the sorted cards. Step 2. Insert a printArray method consisting of a for loop to iterate over each element in the sizes array. The sizes variable represents each coin size during each iteration. The print method will indicate each coin size followed by a space for readability. Outside the for loop, insert a print line statement to view the output on a new line. Step 3. Insert another method and call it selection sort. The length of the sizes array is stored in the variable named length. The for loop starts from the first element, index 0, and iterates through each element in the array up to the last element, or length -1. This ensures that the outer loop controls the boundary between the sorted and unsorted groups of the array. After each iteration, 1 more element is added to the sorted group. The algorithm initially assumes that the first element in the unsorted portion, or counter, is the smallest. The index of this element is stored in min-index. The inner loop will start from the element right after the counter and go to the end of the array. The if statement compares each element in the unsorted group with the current minimum. If a smaller element is found, the min-index is updated to this new index as indicated by the new counter. The smallest element, found in the unsorted group, located at min-index, is then swapped with the first unsorted element, located at counter. The value at sizes, min-index, is then temporarily stored in temp and replaced with the element at sizes, counter. Lastly, this element is then stored in temp. The outer loop continues, moving the boundary between the sorted and unsorted groups to the right, one by one, after each iteration until the entire array is sorted. Step 4. Let's view the output. Java sorted the coins just like Ashley did. In this video, you learned that the selection sort method simulated how Ashley sorted her coins. The algorithm repeatedly scanned the unsorted portion of the list to find the smallest element. Although selection sort is easy to interpret and implement, it is not the most efficient algorithm for large data sets. However, its simplicity makes it an excellent choice for small lists or when an easy-to-implement sorting method is needed. Sorting is an essential process in programming. It allows you to organize, prioritize, retrieve, and make sense of information and processes. With sorting, you can also group data for problem solving, optimization, and further processing. There are 3 basic Java sorting algorithms: bubble, insertion, and selection sort. With bubble sort, each element is compared with its adjacent element, and if they are in the wrong order, they're swapped. This process is repeated iteratively until the list is sorted. Insertion sort divides the list into a sorted and unsorted group. An element is taken from the unsorted group and placed in the correct position of the sorted group. This process is repeated until all the elements are sorted. Selection sort selects the smallest element from the unsorted group and moves it into its correct position of the sorted portion. This process is repeated until all the elements are sorted. In this video, you'll compare the 3 algorithms based on time efficiency, complexity, and use cases. Understanding time complexity helps you choose the most efficient sorting algorithm based on the size and nature of the data you're working with. Time complexity indicates an algorithm's time to run with large or complex data sets. In the context of Java sorting algorithms, time complexity describes the efficiency of different sorting methods. Time complexity is described with the big O notation, or big O of n. It provides an upper bound on the growth rate of an algorithm's running time, or memory usage, as the size of the input data increases. The n indicates the size of the input data, or the number of elements in an array. The big O of n denotes a linear relationship between the input size and the time required to process that input, making it straightforward and predictable regarding time complexity. You need to know all 3 algorithms' best and worst case scenarios. Let's explore examples of best and worst case time complexity for the 3 sorting algorithms. The selection sort has the highest time complexity for 5 elements, making it the least preferred option. Let's start with bubble sort. Big O of n denoted the best case scenario, indicating that the list is already sorted and no swaps are needed. For the worst case scenario, the list is sorted in reverse order. Therefore, each element is out of place. Bubble sort will require n-1 passes through the list, with each pass making approximately n comparisons. Therefore, the number of operations is proportional to n multiplied by n-1 divided by 2, simplifying to big O of n squared. In practice, even in a best case scenario, most implementations of bubble sort still perform big O of n squared operations unless optimized with a flag to stop early. It's important to note that bubble sort is rarely used in practice due to its generally poor performance, even with the early termination optimization. So, why perform big O of n squared operations? The nested loop structure of bubble sort, where one loop controls the number of passes and the inner loop performs the comparisons, leads to a quadratic time complexity of big O of n squared. This means that if the input size doubles, the time taken increases 4 times. The second algorithm is the insertion sort. O of n denotes the best case scenario, as the list is nearly sorted. Each new element is placed directly after the previous one, requiring only 1 comparison per element, and the number of operations is linear. In the worst case scenario, each element must be compared with all the previously sorted elements, leading to n comparisons for each insertion. This results in big O of n squared time complexity. Similar to bubble sort, insertion sort has a nested loop structure. The outer loop iterates over the elements, and the inner loop compares and shifts elements to find the correct position, leading to a quadratic time complexity. The third algorithm is the selection sort. Interestingly, selection sort always scans the entire unsorted portion of the list to find the smallest element, regardless of whether the list is already sorted. Therefore, time complexity is always big O of n squared. The algorithm makes n comparisons in each pass to find the minimum element. Since this process is repeated for each element in the list, the total number of comparisons leads to a quadratic time complexity. Let's review the time complexity of the three algorithms. Big O of n indicates a linear time complexity as time grows linear to the input size. This is the best case scenario for bubble sort and insertion sort, where the list is nearly sorted. Big O of n squared indicates a quadratic time complexity with time that grows quadratically as the input size increases. This occurs when the list is not sorted and the algorithm must perform many comparisons, swaps, or shifts. In this video, you compare the time complexity of the three basic Java sorting algorithms. Understanding time complexity helps in choosing the correct algorithm based on the nature and size of the data, allowing for more efficient sorting in practical applications. Insertion sort is often the best choice for small or nearly sorted datasets because it can perform close to big O of n. Bubble sort is also effective for nearly sorted lists, though it is generally slower than insertion sort due to more comparisons and swaps. Selection sort is straightforward, but consistently slower with the time complexity of big O of n squared, regardless of the dataset's initial order. Happy coding! Imagine trying to sort thousands of files on your desk one by one, comparing each to the others. You'd quickly realize it would take days to finish. This is why having efficient sorting methods is so crucial. You'd have different ways to sort them. One way would be quicker than others, and each way would be an algorithm for sorting. In the last video, you learned about simple sorting techniques. If you are unsure how sorting using bubble sort, selection sort, or insertion sort is accomplished, then pause this video and revise the previous module until you understand sorting. In this video, you'll learn about the need for more efficient sorting algorithms when dealing with large datasets. For comparison, let's start with the limitations of basic algorithms like bubble sort. You're probably familiar with bubble sort, which compares adjacent elements and swaps them if they're out of order. It's suitable for small datasets, but slows down as the number of elements increases. This graph illustrates the time complexity of bubble sort in relation to data size, with the x-axis showing dataset size n and the y-axis displaying time complexity. The orange line shows the best case scenario, order of n with a sorted dataset, while the curved black line, representing order of n squared, represents the average and worst cases, which overlap due to identical growth in complexity when the data isn't sorted. The issue with bubble sort is its time complexity, the order of n squared. As the number of items in your array increases, the time it takes to sort them grows exponentially. Bubble sort is manageable for a small list, but when dealing with thousands or even millions of elements, the number of comparisons can quickly reach the millions, making it impractically slow. You would not like to sit for hours to sort some data now, would you? Let's create a Java program to measure the time bubble sort takes to sort different dataset sizes. To explore the impact firsthand, you'll compare its performance with small and large arrays. Here is the bubble sort performance class, which contains a method named bubble sort. This method implements the logic of bubble sorting on an array of integers. Let's move to the main class and code a method for generating an integer array containing random numbers. For this, type public static int square brackets generate array parenthesis int size curly braces. The method will return an array of integers with the size specified as the argument. Inside the method, create a new array named numbers with the specified size. Now write a for loop that starts at index 0 and goes up to less than size and increment the index. Inside the for loop, you'll use the random method from the math class to generate random numbers. So, type numbers, square brackets, index equals math dot random parentheses multiplied by 10,000. The random method returns a double value between 0.0 and 1.0, and multiplying it by 10,000 scales the range between 0.0 and 10,000.0. Because you're trying to store it as an integer, there's an error at line 5. Hover over the red squiggly line and click on the suggestion given by IntelliJ. Cast expression to int, and the error is gone. Notice the int inside parentheses at line 5 before the math.random. This is called typecasting, which forcefully changes the data type of a value returned from a method. Next, let's return the generated array. After the closing curly braces of the for loop, type return numbers. Now the main class. Create a method named generateArray, which accepts the size of an array in order to generate some random numbers, which it stores in an array named numbers, and then returns the array to where the method generateArray was called. We will use this array of random values to sort using bubble sort logic. Inside the main method, define an integer array named smallData and call the generateArray method with 100 as an argument to create a small dataset. Similarly, define another integer array named largeData and call the generateArray method with 10,000 as an argument. To measure bubble sort's performance, you must measure the time the algorithm takes to sort both datasets. For this, you must compare the start and end times while sorting. Before calling the bubble sort method on the small dataset, let's use the system class's currentTimeMillis method to record the current system time in milliseconds. The method returns a long value, so type long start time equals system dot current time millis parenthesis. Now, call the static bubble sort method from the bubble sort performance class using the dot operator and pass small data as the argument. Record the end time as long end time equals system dot current time in millis parentheses. Next, write a print statement that says double quotes time taken to sort a small dataset is space plus parenthesis end time minus start time plus double quotes milliseconds. Similarly, let's perform bubble sort on the large dataset. Record the start time, call bubble sort with large data, record the end time, and print the time taken to sort a large dataset. Finally, let's run the program and observe the output. As expected, the time taken for the small dataset is reasonable, but notice how much longer it takes to sort the larger dataset. Why is this? This is because of the quadratic growth of time with increase in size. This performance difference highlights why bubble sort isn't suitable for large datasets. In this video, you learned that bubble sort is a great algorithm for a small collection, but has its limitations as the dataset size increases. Other simple sorting algorithms like selection sort and insertion sort also have drawbacks, although we just used bubble sort for comparison. This is why in real-world applications, more efficient sorting algorithms are needed to handle large amounts of data more effectively. Later, you'll explore these more advanced algorithms, which will help you understand when and how to use them in your projects. Have you ever tried to sort a massive stack of papers? Imagine breaking it into smaller piles to make it easier. That's the idea behind merge sort, a divide and conquer algorithm that efficiently sorts data. In this video, you'll explore merge sort in more detail. You'll also gain insight into recursion, a key concept in merge sort, and see how it works. Recursion is when a method calls itself to solve smaller parts of the same problem. It's like standing between two mirrors facing each other. When you gaze into one, you observe a reflection within a reflection, each smaller than the last. This continues until the reflections can't get any smaller. Let's say you want to calculate the factorial of a number n, the product of all positive integers up to n. You define a factorial method that takes an integer as an argument. At line number 7, the method keeps calling itself with a smaller n until it reaches 1 or 0, the base case. Like how the reflections eventually stop, recursion stops when it reaches the base case. Now let's examine merge sort in more detail. Merge sort uses a divide and conquer approach, breaking a larger problem into smaller, manageable parts. First, it splits an array into 2 halves and continues dividing until each subarray has only one element. Why is the splitting done until each subarray has only a single element? Because single elements are always sorted. For example, if you were the only person in the world, you would be the most beautiful until a comparison comes in, right? This means an array or subarray of only one element is inherently sorted. Then, the sorted subarrays are combined or merged together to form sorted subarrays step by step. This allows you to combine sorted subarrays to derive the next sorted subarray, which is a combination of 2 subarrays until you get all the elements of the original array in sorted order. The divide step recursively splits the array, while the conquer step merges the sorted pieces back into one. Now that you've got the basics down, let's jump into coding. Start by creating a new Java project called Merge Sort Demo. Then, add a new class named main inside the project. In the main class, create a public static void method named merge sort. You'll apply the divide strategy in the merge sort method, which must take an integer array as an argument. Remember to provide the left and right integer arguments to specify the array section to process. Left is the starting index, and right is the ending index of the array portion to work on. At this point, it will be good to check whether the array is null or contains 0 elements, in which case you do not need to perform the sorting. Let's add a condition for this. Before dividing the array, use an if statement to check if the subarray has more than one element by comparing the left and right indices. If not, the subarray has only one element, serving as the base case to stop further division. Determine the midpoint as parentheses right minus left divided by 2 plus left and store the result in a variable. You can calculate the midpoint by adding left and right directly and dividing by 2. But this can cause an overflow if their sum is too large to fit in an integer. Now, recursively apply merge sort to the left and right halves. For the left half, type merge sort parentheses numbers, comma, left as the starting index, comma, middle as the ending index. For the right half, type merge sort parentheses numbers, comma, middle plus 1, comma, right. With the division complete, it's time to merge the array's 2 halves, including the middle element. Call the merge method assuming it's already defined by typing merge parentheses numbers, left, middle, right. Don't worry about the error on line 10. It will disappear once you define the merge method. Define the method as public static void merge with arguments integer array int left, int middle, int right, and curly braces. The merge method is where the conquer strategy comes in. Start by calculating the sizes of the 2 subarrays. The size of the left array is calculated by subtracting the left from the middle and adding 1. The size of the right array is calculated by subtracting the middle from the right. Declare 2 temporary integer arrays, left array and right array, with the calculated sizes to hold the values of the subarrays. Now, copy the data to the temporary arrays using for loops. The first loop starts at 0, goes up to size of left array, and copies the elements as left array of index equals numbers of left plus index. The second loop starts at 0, goes up to size of right array, and copies elements as the right array of index equals the numbers of middle plus 1 plus index. The indices are adjusted based on left, middle, and right to ensure the correct elements are copied. Finally, merge the temporary arrays into the original array numbers. Declare index of left array equals 0, index of right array equals 0, and index of merged array equals left because you merge the array from the left index. For merging, loop through the left and right arrays such that the index of the left array is less than the size of the left array and the index of the right array is less than the size of the right array. Compare the current element of left array and right array and place the smaller element into the numbers array at index of merged array. Increment the respective indices so that the process continues until one of the temporary arrays has exhausted. Use 2 while loops to copy any remaining elements in the left and right arrays. Finally, create a main method to use the method. Start by creating an integer array named numbers containing, say, 7 elements. Print all the elements of the array using a for loop. Call the merge sort method and pass the numbers array, with 0 as the left index and numbers.length -1 as the right index. Print the sorted array to confirm if the method works as expected. Finally, run the program and observe the output. You'll notice that the array is sorted successfully. In this video, you learned about merge sort using a divide and conquer approach. Just like breaking your large stack of papers into smaller piles, it makes sorting easier. Now, try implementing it on your own with different arrays. Recursion might seem tricky initially, but with practice, it becomes a powerful tool in your coding arsenal. Imagine you're working at Click and Buy, where every second counts when processing thousands of transactions per minute. Sorting this massive amount of data quickly and efficiently is crucial to running the system smoothly. But how do you ensure that your sorting algorithm can handle large-scale tasks without slowing everything down? In this video, you'll analyze the time complexity of merge sort compared to bubble sort to determine which sorting algorithm will optimize their system's performance as they prepare to handle a massive influx of transaction data during an upcoming sale event. Let's get started by examining time complexity in more detail. Time complexity measures the amount of time an algorithm takes to complete as a function of the size of the input data. Time complexity is a crucial factor in algorithm analysis because it helps predict how an algorithm will perform as the data size grows. Big O notation is the standard way to describe time complexity. Big O categorizes algorithms based on their worst-case performance. Common time complexities include O of 1, O of n, O of n log n, and O of n square. Each represents a different relationship between the input size and the time taken by the algorithm, affecting how well the algorithm scales with increasing data sizes. Now let's explore the time complexity of merge sort. This can be expressed in O notation as O of n log n, where n is the number of elements. N means that the algorithm will process each element at least once, leading to n operations. So this means that the algorithm will perform n operations for log n levels of processing to sort the elements. For merge sort, the time complexity is O of log n for best, worst, as well as average performance. As the size of the input data increases, the time it takes to sort the data grows at a rate proportional to n log n, where n is the number of elements. For example, if there are 1,000 elements, then the time complexity calculator would look like this. O of n log n, 1,000 log 1,000 equals 1,000 times log 1,000, which equals 9,966 iterations. Now let's compare the time complexity of the merge sort to that of the bubble sort and insertion sort. The time complexity of the insertion sort is the same as the bubble sort, which is O of n square, meaning that the number of iterations is the number of elements squared. In practice, however, the time complexity is not always the square of the number of elements, because of the input values like an already sorted array. Instead, it's the number of elements times about half the elements. So, if there are 1,000 elements, the calculation would look like this. O of n squared equals n times n minus 1 divided by 2. 1,000 times 1,000 minus 1 divided by 2 equals 1,000 times 499.5, which equals 500 iterations. That is a huge difference compared to the merge sort, which would require only about 9,970 operations for the same number of 1,000 elements. As the number of elements increases, the disparity in speed also increases. For example, if you have to sort 100,000 elements, this is how the sorting algorithms compare. For merge sort, O of n log n, 100,000 log 100,000 equals 1,660,964 iterations. And for bubble and insertion sort, O of n squared equals 100,000 times 100,000 minus 1 divided by 2, which equals 4,999,950,000 iterations. That's 1.66 million iterations for the merge sort, compared to nearly 5 billion for the bubble and insertion sort algorithm. That's more than 3 orders of magnitude difference. Merge sort is particularly efficient for large datasets because it consistently divides the data in half and processes each half separately before combining them in a sorted manner. This efficiency makes the preferred choice for scenarios where predictable and stable performance is crucial, such as in large-scale data processing tasks at companies like Click and Buy. In this video, you gained an understanding of the time complexity of merge sort and how it compares to bubble and insertion sort algorithms. You learned that merge sort is highly efficient for large datasets, making it an excellent choice for scenarios like those faced by the engineering team at Click and Buy. In contrast, while bubble sort is straightforward to implement, it is less suitable for large-scale data processing. Remember, selecting the right algorithm for your needs is crucial in optimizing performance and efficiency. By understanding the strengths and limitations of different sorting algorithms, you can make informed decisions that enhance your system's reliability and speed. Imagine you're managing a warehouse for Click and Buy, where items need to be organized quickly. Quick Sort works like a skilled team, efficiently placing each item without wasting time or space. Quick Sort is a fast, in-place sorting method that uses minimal memory to get the job done. In-place sorting is a technique that uses a rearrangement of elements within the original array to derive the sorted array, without needing extra memory or another array for storing the array elements. In this video, you'll learn how it works, focusing on its partitioning method and recursion. You'll also learn why it's a go-to solution for memory-limited environments. Let's get started. Click and Buy, an online retail company, needs an algorithm that sorts product listings quickly without overwhelming memory, ensuring a seamless user experience. Quick Sort is a highly efficient sorting algorithm that uses a divide and conquer approach. Firstly, it selects a pivot element. There are different common approaches to selecting the pivot, including first element in subarray, the last element in the subarray, the middle element of the subarray. You will use the option of selecting the middle element, as this can avoid worst-case performance for arrays which are sorted or sorted in reverse order. The pivot element is used to partition the array into 2 subarrays or 2 halves, one with elements smaller than the pivot and one with elements greater than the pivot. Next, it repeats the process recursively for each subarray, allowing Quick Sort to sort the data efficiently in place, making it ideal for memory-constrained applications. The process continues until the array is sorted. It helps to see how Quick Sort is implemented in the code to gain a better understanding. Let's dive in. At the heart of Quick Sort is its partitioning process, which is performed by the partition method. The low and high int values are inclusive indexes of some subset of the original array. The algorithm selects a pivot element with the subset of elements. The pivot can be the first, last, or random element within the low and high indexes. In this case, it uses the high index, the last element in the subset of elements. The algorithm then loops through the elements from the low index to the high index, moving all the elements less than the pivot to the left and all the elements greater than the pivot to the right. This swapping is accomplished using the pivot, a local variable I, and the for loop variable j. Notice that the local variable I starts out one less than the low index. If the low index is 5, then I starts out as 4. If it's 0, I starts out as -1. The local variable I is incremented every time an element less than the pivot element is found. If at the end of the for loop I equals the -1, it means that none of the elements were less than the pivot element. If the value is less than the pivot element, then the I value is incremented, and the element that is less than the pivot is swapped with whatever is at I. When the for loop is done, I should be equal to the last index that was swapped. This means all the elements left of I are less than the pivot element, and everything right of I is greater than or equal to the pivot element. After the for loop, the algorithm swaps the value at I with the value at the pivot. Not all the elements are sorted at this point, but after this last swap, you know that everything left of the pivot element is less than the pivot. Finally, the partition method returns the index value of I plus 1. That return value will be used to determine the low and high indexes of the next subset of elements. The important thing to remember is that the partition method will be called repeatedly on the same array, changing the subsets that are sorted until the entire array is sorted. This is accomplished using recursion. Remember that recursion is when a method calls itself. The result can be powerful, but it is also potentially buggy. If you need a refresher on recursion, review the merge sort overview video. When you're up to speed, return to this video and pick up where you left off. Now let's get back to coding. The partition method is called by the quicksort method, which is itself called by the main method. The process starts when the main method passes an unsorted array, including its start and end indexes, to the quicksort method. When the program first executes, the full array is passed to the partition method. Next, the partition method returns a partition index. This partition index is used to break up the original array, now partially sorted, into 2 segments. Each segment is passed recursively to the quicksort method. One segment starts at 0 and goes to the pivot point, and another starts at the pivot point and goes to the end of the array. These recursive calls can go on for a while. In the previous code demonstration, the quicksort method is called 13 times to sort an array of 8 elements, with a recursion depth of 3. It is important to remember 2 things. 1, the number of recursions is not as important as the depth of recursion, and 2, log n in O of log n refers to the log n or logarithmic depth of recursion in the most ideal scenario. So, 8 elements will have depth of 3. Why? To understand this, you must understand the term logarithm, otherwise known as log. Logarithm or log answers the question, what powers must a base be raised to get a number? And remember, the base in computer science is always 2. So if there are 8 elements, the base 2 must be raised to the power 3 to get 8, and so the depth of recursion will be 3. Similarly, for 24 elements, it will be a depth of 5, because 2 to the power 4 is 16, and therefore falls short of 24. But 2 to the power 5 is 32, which can accommodate the value of 24. As such, to sort 24 elements, we would have a recursive depth of 4. Let's return to the code one last time to view the fully sorted array. Running the application's main method results in the following output that shows that the array is fully sorted. Let's explore the advantages of quicksort. Quicksort's average case time complexity is O of n log n, making it faster in most cases than many other algorithms, such as bubble sort. However, remember that the worst case time complexity is O of n square. Unlike some other algorithms, quicksort can handle large datasets. Additionally, because it sorts in place, it doesn't require extra memory, making it particularly useful in memory-constrained environments. At Click and Buy, the developers chose quicksort to process thousands of records quickly and efficiently. The speed at which it sorts helps to create a satisfying user experience, or UX. In addition, it reduces costs by requiring less memory and fewer processors. However, there are some performance considerations. While quicksort is usually efficient, its worst-case time complexity can degrade to O of n squared when poor pivot choices are made. However, this can be mitigated by choosing a pivot wisely, such as a random pivot or using the median of 3 method. You'll learn about these methods in more detail later. In this video, you learned about quicksort and its efficiency in real-world applications. You explored how the partitioning and recursive processes enable quicksort to handle large datasets efficiently, making it ideal for memory-sensitive tasks like real-time sorting. Keep exploring other sorting algorithms to expand your toolkit and further enhance your coding skills. At Click and Buy, the team is considering quicksort to handle high transaction volumes. They want to understand its performance, as it's usually fast but can face occasional challenges. In this video, you'll dive into the time complexity of the quicksort algorithm. You'll examine its average O of n log n performance and worst-case O of n squared scenario. You'll also explore ways to avoid the worst-case situation and ensure optimal performance when dealing with large data sets. Let's get started. First, let's recap on what you learned about time complexity. Time complexity measures the time an algorithm takes to complete as a function of the input data size. It is a crucial factor in algorithm analysis because it helps predict how an algorithm will perform as the data grows. Big O notation is the standard way to describe time complexity. It categorizes algorithms based on their worst-case performance. Common time complexities include O of 1, O of n log n, and O of n squared. Each represents a different relationship between the input size and the time taken by the algorithm, affecting how well the algorithm scales with increasing data sizes. In the average case, quicksort operates with an efficient time complexity of O of n log n, the same as the merge sort, making it well suited for large datasets. However, in the worst-case scenario, its time complexity can degrade to O of n squared, significantly slowing down performance. That is a huge difference. As the number of elements increases, the disparity in speed also increases. Quicksort is a divide-and-conquer algorithm that selects a pivot element, partitions the array into subarrays around the pivot, and recursively sorts the subarrays. The efficiency of quicksort depends mainly on how balanced the partitioning is. Well-balanced partitions lead to faster sorting, whereas unbalanced partitions can degrade performance. In this example, you select the pivot point as 300 between the smallest value of 150 and the largest value of 500. As a result, it's a well-balanced pivot, and the sorting is done quickly. Quicksort's worst-case time complexity occurs when the partitioning is highly unbalanced. This occurs when the chosen pivot consistently results in one subarray containing only one element and the other containing the remaining n-1 elements. In this situation, the algorithm performs O of n partitioning operations n times, leading to an O of n squared time complexity. This worst-case scenario is especially problematic when sorting large datasets, as it can significantly slow down performance. However, unbalanced partitioning is avoidable. You can apply one of two optimization techniques to prevent quicksort from degrading to its worst-case time complexity of O of n squared, randomized pivot selection, or median of 3 partitioning. By randomly selecting the pivot element, you reduce the chance of consistently picking poor pivots that result in unbalanced partitions. Let's explore how the random pivot selection is done in code. You learned previously about the code required to implement the quicksort. Let's use that same code base, but with one modification. To implement the random pivot selection, you need to change the call to the partition method from the quicksort method to an intermediary method, random partition. The random partition method creates an instance of the Java util random class. It then uses that instance to select a random pivot index from between the low and high indexes. Then it swaps the randomly chosen pivot element with the element in the past position so that it can call the partition method, which has not changed since it was demonstrated in the quicksort overview video. The partition method looks like this. You can run this modified quicksort from the main method. The end result is that the output is sorted by a well-balanced quicksort algorithm. The median of three partitioning technique chooses the median of the first, middle, and last elements of the array segment as the pivot, ensuring a more balanced data partitioning. Let's examine how this is implemented in the code. Using the code from the quicksort overview video as a base again, you'll notice that the quicksort method has not changed. It still calls the partition method and then recursively calls itself. It's the partition method that is different. Before the partition method starts to sort the array, the median of three method is called. In the median of three method, the first step is to find an index approximately the middle index of the array subset, bound by the low and high indexes. Next, the values at the low, mid, and high indexes are compared to determine which value falls between the other two values. If the value at the mid index is greater than the value at the low index and less than the value at the high index, then the value at the mid index is your median value. This should be the pivot point. Since the partition algorithm assumes that the pivot is the last element, you swap the median value at the mid index with the value at the high index. If, however, the value at the low index is between the other two values, then it's swapped with the value at the high index. Finally, if the value at the high index is between the other two, then it's exactly where you want it, and no swapping is done. After ensuring that the median value is in the last index, you return that value as the pivot value. That value is then used in the partition method to sort the elements, just as it did in the quicksort overview video. You can run this modified quicksort from the main method. The end result is that the output is sorted by a well-balanced quicksort algorithm. In this video, you explored quicksort's O of n log n time complexity, which makes it efficient for large datasets like those faced by the Click and Buy team. Choosing the right algorithm is key to optimizing performance, so keep exploring to sharpen your software development skills. At Click and Buy, the dev team has a problem. They're swimming in data, customer purchases, inventory updates, search results. It's a lot. And they need a way to sort it all quickly to get the platform working at peak performance. To this end, they're debating between two algorithms, merge sort and quicksort. Should they go with merge sort for its consistency and stability with big data, or quicksort for its speed and in-place sorting? Let's dive in and find out. In this video, you'll compare merge sort and quicksort, going over their pros and cons to see when it's better to use one over the other, especially when working with large datasets or needing in-place sorting. Before comparing, you need to understand how these algorithms actually work. So, let's dive into each. First up, merge sort. Merge sort is a divide and conquer algorithm. It divides the input array into smaller subarrays until each contains a single element. Then, these subarrays are merged in sorted order. It is known for its time complexity of O of n, log n in all cases, best, worst, and average, making it a stable and predictable sorting algorithm. However, merge sort's disadvantage lies in its space complexity. Since it creates copies of subarrays during the merging process, it requires O of n additional space. Now let's take a look at quicksort. Quicksort is another divide and conquer algorithm, but differs in that it sorts in place, meaning it doesn't need extra memory. It selects a pivot element and partitions the array so that elements less than the pivot go to one side and those greater go to the other. While the average time complexity is O of n log n, its worst case time complexity is O of n squared if the pivot selection is poor. This is if the pivot is the smallest or largest element repeatedly. The benefit of quicksort is its in-place sorting, making it more memory efficient than merge sort. But what does this mean for Click and Buy? As you know, their dev team is facing a data challenge. They need to optimize the sorting of large datasets to improve platform performance. So, which algorithm should they choose? Merge sort is stable and works great with large datasets, but it needs more space for its operations. In other words, more memory. On the other hand, quicksort is faster in many cases and sorts in place, meaning less memory is necessary. However, its performance can degrade significantly with certain types of data. The dev team knows both algorithms have strengths and weaknesses, so they must consider the best fit for their task. The bulk of their data is inventory records and customer purchase history, so perhaps each dataset's unique aspects will help them decide. Let's take a closer look. Take Click and Buy's inventory records, for example. These large static datasets don't change frequently, but must be sorted regularly to keep the platform running smoothly. This data is critical for updating product listings, managing stock levels, and ensuring products appear in the correct order. Merge Sort is a great choice for this kind of data because it's stable and maintains the relative order of records with equal keys, crucial for businesses like Click and Buy, where items may need to be sorted by price but displayed in order of entry. Merge Sort also consistently handles large datasets well with its O of n log n time complexity in all cases, best, worst, and average, regardless of whether the data is already sorted or not. Finally, Merge Sort is also perfect for external sorting, where the dataset is too large to fit into memory. It splits the data into smaller chunks, sorts them individually, and then merges them back together, which makes it ideal for large-scale data processing even when memory is limited. On the other hand, Click and Buy's customer purchase history is a different story. This is a dynamic dataset that changes constantly as new purchases are made. This data requires efficient, in-place sorting with minimal memory overhead. Quicksort's in-place sorting is a big advantage because it doesn't need extra memory, which is important when handling real-time data where memory usage must be optimized. Additionally, Quicksort's fast average performance, due to lower constant factors, is more than enough to handle continuously updating data, like customer orders. So, after all that, Click and Buy's dev team discovered they could use both algorithms for different datasets and contexts that best suited each algorithm's strengths and advantages. With Click and Buy's problem solved, you now understand Merge Sort and Quicksort and learned how to compare these two algorithms in terms of their efficiency, stability, and memory usage. You can now confidently decide when to use each algorithm based on specific scenarios and data needs. Keep practicing to deepen your understanding. Soon you'll be sorting like a pro. Congratulations on finishing the Searching and Sorting Algorithms module. You have covered a wide range of topics and built a solid foundation in understanding and implementing some of the most essential data structures and algorithms in Java. In this video, you'll recap the key concepts and skills you've gained and revisit how they supercharge your ability to handle complex datasets in Java. First, a quick summary. In this module, you'll learn to use hash maps, linked hash maps, and tree maps for efficient data storage and retrieval in Java. You also explored linear and binary search algorithms, boosting your data search approach. You also applied sorting methods like bubble, insertion, and selection sort, along with more advanced merge sort and quicksort methods to handle larger datasets efficiently. All these tools help improve app performance. You started the module focusing on hash maps, linked hash maps, and tree maps. You learned how these structures allow you to store, retrieve, and manipulate data efficiently. Hash maps gave you a powerful tool for fast access to key value pairs, while linked hash maps introduced you to maintaining insertion order, an important feature when order matters in your application. Then, with tree maps, you discovered how sorting your data can be done automatically through red-black trees. By examining the different use cases and performance characteristics of each map type, you got an idea of the best data structure for specific needs. Plus, by practicing with code, you become better at selecting the right tools for robust data management. Onward into Lesson 2, you tackled the searching algorithms. You now know how to use both linear search and binary search to find elements in a dataset. More specifically, linear search showed you how to search through data step by step, while binary search introduced you to the divide and conquer strategy, demonstrating how much faster you could find items in a sorted list by repeatedly splitting the data in half. By the end of Lesson 2, you'd gained some new skills in implementing both linear and binary search. You didn't stop there, though, as you also compared their efficiencies, understanding when to use each approach based on the structure of your data. Next, in Lesson 3, you learned about the bubble, insertion, and selection sort algorithms. These foundational sorting methods showed you how to arrange data in an orderly fashion, each with its own strengths and trade-offs. Bubble sort helps you get a feel for basic sorting by repeatedly comparing and swapping adjacent elements. Then, Insertion Sort and Selection Sort expanded your sorting toolkit, showing you how different approaches can lead to better efficiency in various scenarios. By experimenting with these algorithms, you got some insight into how time complexity, the amount of time an algorithm takes to run as a function of the input size, plays a role in algorithm performance. Finally, Lesson 4 took it up a notch with merge sort and quick sort, algorithms vital for adequately handling large datasets. With merge sort, you revisited the divide and conquer approach, breaking data into smaller parts to merge them back together. Quick sort, with its partitioning method, gave you another high-performance option for sorting. You also compared their pros and cons, learning when to choose one over another depending on the size and complexity of your dataset. And that was that. Great work. Now that you've completed this module, take a moment to reflect on how far you've come. You've learned how to manage data with maps, search through it with algorithms, and sort it with efficiency in mind. These skills will greatly enhance your ability to build optimized and high-performing applications. Keep up the momentum, and don't forget to revisit these concepts whenever you need a refresher. The more you practice, the more these algorithms and data structures will become second nature.